Hello and welcome to another repair video. Today I have here a 486 mainboard made by Soyo. It has to be dead. I made a short test a long time ago and put it into my to be repaired box, where it was stored until today. Unfortunately, I didn't make a note what was wrong with it, so let's take a look. Every repair has to start with the search for the documentation. I didn't know anymore which mainboard model it was exactly, but I could locate it on the Ultimate Retro project. I just had to enter the data I knew, like the manufacturer name Soyo, 3 VLB slots and 7 16-bit ISO slots. The CPU socket is socket 3. When searching by image, it is usually just a matter of seconds to find the right model. And in this case, the model version is either Soyo SY-025Q or 25R. I'm not sure, but I guess the R in the name stands for the voltage regulator. Probably this mainboard was delivered also without a voltage regulator, but the variant which I have here is equipped with one, so I guess the name of this board has to be SY-025R. Luckily, Ultimate Retro had even the scan of the original documentation, so I should have all the information I need to set the jumpers properly. But first of all, let's take a brief look over this board. It is actually quite a good one. This board has 3 VLB slots as well as 256K of 15 nanoseconds fast level 2 cache. Both are nice to have features for a fast machine with a good graphics card. And it also supports 30 and 72 pins FPM memory modules. And as I already mentioned, it has a voltage regulator, so this board should support 3-volt CPUs as well. All in all, these mainboards would provide a solid base for a very nice 486 retro build. On the bad side, unfortunately, is that it was damaged by a leaky battery. Luckily, none of the traces were damaged. There is some corrosion visible, but as you can see, there is still continuity. The one trace is the keyboard clock signal, the other one is data. I will have to come back to this damage, remove the keyboard connector, clean the oxidation and enforce the traces again, but for a test it looks good enough. Off camera I already set the jumpers to 5 volts and 33 MHz FSB. First of all, let's check the CPU voltage. And as you see, we have 5 volts. 1 square means 2 volts and we have 2.5 squares. 2 volts, 4 volts and a half means another 1 volt, so 5 volts in total. That looks good. Now let's check the clock. I just have to reinsert the cable into another pin in the socket. Yep, looks good. There we have 33 MHz frontside bus. Time to insert the CPU. I am going to use this 486 DX266 with a cooler glued on top of it. Off camera I already set all the jumpers as required. So we will need a post analyzer card and a PC speaker. Let's give it a try. Okay, that is a good sign. The post analyzer shows some numbers and the PC speaker notifies missing memory with the long beeps. Let's add some memory. I have here an 8MB FPM module with parity chips, which I usually use for testing of 486 mainboard. Okay, there is silence. I would expect some beep codes complaining about a missing graphics card. The last postcode is 0D. Let's see in the manual what this postcode means. The codes differ for various BIOS manufacturers and it is always important to look up the codes for the right one. The inscription on the BIOS IC of this mainboard stands a word. So we are searching for the postcode 0D for a word. Oh, look at that! The board awakened. Seems to be a constant beep. I have no clue what this means, so let's continue to search for the code. Oh, now the beeps changed again. 0D stands for the CPU clock and or video adapter detection. Oh, look, the code has changed to 42. That would be the answer to life, the universe and everything, but unfortunately it is in hexadecimal, so we have to search further. And it says hard drive controller initialization. That makes somehow no sense for me. Well, if such strange things happen, it is worth to double check the BIOS. Let's read it with a programmer. The BIOS IC is a Texas Instruments TMS27C512. Yeah, looks like there is something valid inside. Let me save this dump and open it with a tool named modbin. And if you don't know what modbin is, then I suggest to watch a video about BIOS modding tools on the YouTube channel Atheatos. A great channel if you are into retro DIYs, modding and overclocking. The required version of the tool modbin for this 486 BIOS is 4.50. It is a very old DOS tool and I always use it in DOSBox. I saved the BIOS dump previously under the name of the IC, TMC27C, etc. Let's load it and see what we will find. Okay, down here we have version 303, but up here is something really suspicious. This is so-called post string, which is usually shown on the bottom of the post screen. And in this case we see VT82C486A in the middle. It is a model of a VIA chipset, which can be found on many 486 mainboards. What is the problem, you may ask? Well, the problem is that this mainboard is built around a UMC chipset and not VIA. I don't remember anymore where I got this mainboard from, but this is why I don't like to repair hardware which someone already tried to repair. Someone took a BIOS ROM and put it into this mainboard, despite that it is completely incompatible. Here is an image of a mainboard with the named VIA VT82C486A chipset, and take a look at the BIOS IC. Do you see this 303G? This chip looks the same like the one which was inserted into the Soyo mainboard with the UMC chipset. What a sneaky trap someone left behind. Okay, let's get the BIOS dump from the Ultimate Retro project. There is only one version available and the name is Rev-A. Back into modbin, let's load the BIOS. Yeah, much better. The post string contains UMC 498GP. This looks a lot better, so let's write it to a clean EEPROM and give it a try. In case that was sufficient, I will directly add a VLB Cyrus Logic graphics card, an IDE controller and a compact flash card with DOS, tools and other software. And would you look at that? The mainboard initializes properly. You can see the Rev-A version of the BIOS and down here the mentioned post string with the UMC in it. Let's enter the BIOS and set up the compact flash card geometry. The card is a 512 MB one with 987 cylinders, 16 heads and 63 sectors. I will deactivate the floppy drive since I didn't even inserted a floppy controller. Here I will leave everything at defaults except the boot sequence. The system shall not try to boot from a non-existing floppy. In the chipset feature setup there are not really many options, to be honest. I'll leave everything at defaults as well. Oh, and here is already something wrong. The system information shows that there is no level 2 cache installed. I am pretty confident that the jumpers are all set properly, so there must be something else going on. At least we are in DOS. So far so good. Let's take a look at sysinfo. Here everything looks alright. Let's take a look at the benchmark. Oh boy, this is far too low for a DX266. We should get around 144 points and not 96.6. Looks like the cache doesn't work indeed. The best way to confirm it is to use speedsees. Yeah, the CPU gets 24 points. That is not quite as good as a DX266 should run. But here on the right, the fear is confirmed. There is no level 2 cache at all. You can see only one performance slide at 8 kilobytes. This is the internal level 1 cache of the CPU. And after that, the lines remain flat. Let's see if there is an option in BIOS to activate the level 2 cache. Back into BIOS feature setup. Here we have only an option for the internal level 1 cache, but no level 2 cache options whatsoever. In chips feature setup, there are no settings for the level 2 cache as well. Okay, back into BIOS modification utility modbin. The 25Q25R.bin is the file which I downloaded from the Ultimate Retro project. As you see, rev A down here and UMC in the post string. I will try to make some changes to the BIOS, but first of all, to distinguish this BIOS from the revision A, let's change the name. Now we should see the message modified by Necroware using this BIOS. I will not go into details on each entry here. There are some chipset configuration, registers, options, etc. You shouldn't touch that settings unless you really know what you are doing. For now, I'm only interested in chipset setup defaults menu. But before entering it, there is an option to show how the actual BIOS will look like with current settings. Pressing F2, we will land in the BIOS preview, and here you can see the entries which we already have seen before in the actual hardware. Let's take a look into the entry BIOS features setup. Notice that there are no settings for any cache whatsoever. Now compare this with the image from the manual. Do you see those options for internal and external cache? Let's see if we can get those options into our actual BIOS too. As I said, the menu we are interested in is the chipset setup defaults. In this list on the left, you can find all kinds of entries like standard CMOS setup, BIOS feature setup, chipset feature setup, and so on. These entries are the same which you could see in the BIOS, and as you see, some of those entries like power management setup, for example, are disabled. Let's change it from disabled to normal by pressing plus on the keyboard and get back to the BIOS preview once again. On the first side here, nothing has changed. Or did you already spot something? This load setup defaults Top menu entry looks odd, doesn't it? Let's switch to it. Whoops, did you see how it changed to power management setup? Exactly the same entry which I activated previously in the settings. The reason why we saw that strange default stop is because two menu entries obviously were covering each other. Let's see how we can fix it. On the right here you can see the X and Y columns. Those define the positions of the entries in the menu. X can be chosen from two values, LT and RT, where LT stands for the left tile and RT for the right tile. So you can basically control which menu entry will occur on the left and which on the right. The Y coordinate is the vertical line, so in this case standard CMOS setup will be placed in the left tile on the line 4. The password settings on the right tile, also on the line 4. So, as you see, the power management setup and the load setup defaults menu entries both share the same coordinates on the left tile on the line 10. Let's change the load setup defaults to 11 and go back to the preview once again. Yeah, and there you see both entries not covering each other anymore. However, the distribution of the entries looks wrong, since they take every second line. So let's fix that. Here you can see the Y coordinates at 4, 6, 8, etc. every second line. So let's change the line for load setup defaults to 12 and check the preview once again. And voila! We successfully added a new entry to the main BIOS menu. And the spacing seems to be right now as well. So let's head on and see which options we can add into the setup submenus. I don't think that we would need to change anything in the standard CMOS setup menu, but we definitely will need some new entries in the BIOS features setup, as we're still missing the settings for the cache. Okay, let's go back into the BIOS editor and see which options we have. You can switch between the menus using page up, page down buttons. First comes standard CMOS setup. As I said, I don't think that we will have to change anything here, so let's just jump over to the next one, BIOS features setup. And now it gets really interesting. This configuration window looks similar to the one where we already edited the main menu entries. On the left side, you can see all the possible BIOS entries which can be used in the BIOS features setup. On the most right two columns, you can see the X-Y columns for the layout. Again, LT and RT stands for left and right tile, and Y is the line where the option has to appear. The second column, with all the normal and disabled entries, controls if the given option will be visible to the end user eventually, and the two BIOS and setup default columns define obviously the default values. And the first one we are interested in is, of course, the external cache entry. As you see, the internal cache is set to normal and the external level 2 cache is disabled. Also very important to notice here that the defaults are also set to disabled. So whoever configured this BIOS made the option for external cache not only invisible, but also disabled the level 2 cache altogether, what led to the very low overall performance which we could see previously. And as you see once again in the BIOS preview, there is no entry for the external cache indeed. By the way, you probably already noticed that the option for the level 1 or internal cache is missing either, despite that it is enabled in the configuration. Well, in this BIOS preview window, the internal cache settings are usually not displayed. I guess those bits are somehow dependent on the real CPU to be shown. That's why we will not see it in this emulated preview. Now let's go back and enable the external cache entry. I will also enable the external cache by default. There are seldom cases where you want it to be disabled. Furthermore, we have to adjust the coordinates of the entry. As you see, the external cache and the boot sequence entries have the same coordinates. Both are located in the left tile on the line 6. I will just refer to the manual and place the entries as stated there. Therefore, I have to reorder the entries and move all the following entries by one line. Okay, let's see how it looks like now. And as you see, with a little effort, we could add the setup entry for the external cache. Now I'm going to step through all the menus and restore everything to the same state as it is listed in the manual. Also the DRAM and cache timing settings, as well as most of the other hidden entries which can be helpful for some system tweaking later. I think it is not necessary to go through all that in detail, since I hope that it is clear now how it works. What's left is to write the modified BIOS version to the EEPROM. I loaded the image already into the programmer's software. To validate that this is the version I made, let's search for the string necroware. Yep, as you see, it is the one. Let's program the EEPROM and see if it works. And the good news is, it is still alive. And as you can see, now we have this modified by necroware in the version string. Let's see if the BIOS has now some additional settings to offer. First, let me set up the hard drive again and deactivate the floppy. Now the interesting part, the BIOS features setup. And I would say that we are on the right way. Now there is an enabled option for the external cache. Really nice. Let me set the boot priority from A to C, since there is no floppy connected. And in the chipset features setup, there are also now a lot of new options. I will disable the auto configuration and tweak some settings. I have a fast 16 nanoseconds memory and 15 nanoseconds level 2 cache installed, so I think that we can push everything to the limit. Yeah, this should be good enough. Let's give it a try. Oh, would you look at that! Now we have 256K of external cache. That should make quite a difference. And DOS is booting, that is quite a good sign. Let's head directly to the sysinfo benchmark. And here we are with 144 points against 96 which we had before. Let's see what Speedtest's benchmark has to say now. And now we have a second slope here at 256K, so the cache was definitely detected properly. Furthermore, thanks to the new timing options in BIOS, the throughput could be significantly increased. Memory throughput grew by about 10% and level 1 cache throughput even by about 25%. This is definitely not a world record for a 486, but this system is now quite a lot faster. And as always, I use Doom as an indicator for stability, since it puts quite a lot of load on such a system. If it runs through a couple of times without a crash, you can usually consider the system quite stable. The Doom benchmark could be finished with 2531 real ticks, that is about 29.5 FPS. A pretty good value actually for a 486DX266. Well, off camera I left the benchmark running a couple of times and the system completed it every time absolutely reliably. So the aggressive timing settings in BIOS were not too optimistic. And I'm super glad that this board is back to life. VLB mainboards with 3.3 volts regulators are less common, so it's nice to have it. Fortunately, this board had no further issues except the wrong BIOS IC, which was probably pulled from another incompatible mainboard. But this gave us a reason to talk a little bit about the BIOS modding for such systems. I already uploaded the modified BIOS to the Ultimate Retro project in case you need it. And if you have another mainboard with hidden important options, hopefully you now know what can be done. And for this board, I'm almost done. I will just have to make some minor repair on the traces around the battery damage, but I will do it off camera since I already showed many times how to do that. And this is it from me for today. I hope you found it informative and maybe even a little bit entertaining. Just as always, I'm looking forward for your feedback and say thank you and goodbye.